Well, hello friends, welcome to one more video. In this video, I will particularly be discussing about one more contour integral. So you see, I have written here. This kind of integrals are useful. So 0 to infinity 1 over xs cube. Actually, I will do it for a general n. So you can even manage to evaluate this integral, which itself looks very dangerous. So let's try to see. So you see, let's start with this integral. So 1 plus xs cube equal to 0 will be the roots of this lower part, will be the singularities of this integrand, and you see, so equal to -1, and that is just this with a mod 2 pi phase, and so the roots are of this form. So when m equal to 0, you get a root I pi by 3. When m equal to 1, you get a root I pi. So I've shown here. So you see, the modulus is 1. So this is just e power I pi, and then you can have this point to be the second root. This is the second root. So this is the second root, this is the first root, like that they will go on. So to make our life easier, I will choose such a contour that it has just one root. So we choose a contour that I have shown here. It goes from 0 to an angle of 2 pi by 3. Okay, such that this point is actually let me see, this point is actually r e power 2 pi I by 3. Okay, so let's move on. So the contour integral of this function, so I just complexified the function. That means I just renamed the variable in a nice way as z. So anyway, so this thing will just be 0 to r to 2 pi by 3 arc. So this is there. This arc I just parameterized by z equal to let me see. So z equal to r e power I phi. So I just used this parameter, substituted it here, and then just took the integrand limits. So well, this is this, and then you have the slant part, as in the previous video of Fresnel integral. So this is the slant part, equal to 2 pi I times residue at e power I pi by 3. Only one pole has the residue. The pole itself is a single order pole, or the first order pole. So let us look at 3 points. So slant height, the slant integral is again parameterized in such a way that the integral looks nice. Well, so it runs from r to 0 like this. You can see the parameters. When I put z equal to r e power 2 pi I by 3, I will get t equal to capital R, and z equal to 0, I will get 0. So that's the slant integral. The residue, this is important. The residue is just 2 pi I times limit. Residue itself is just this by definition, z minus z naught times f of z. So this is just z minus z naught times f of z at limit z tending z naught. Both the terms will diverge off to 0. Both will be 0, so I can use L'Hospital to simplify. So differentiating the numerator gives me 1, the denominator will give me 3z square, and then I can put this thing here, so I will get this part. And the c part is just the fact that this arc integral 0 to 2 pi by 3, this guy here will die off. Why will it die off? You see, you take this part, you divide numerator and denominator by r e power I phi. You will get something like this. Now take r tending to infinity. When you take r tending to infinity, this part will die off, this part will blow off, this entire integral will go to 0, because 1 over infinity, I am talking in terms of limits, will go to 0. So finally, after everything, my this integral, this everything got taken care of. This got taken care of in part C, this got taken care of in part B, this got taken care of in part A. Finally it will give me this line. You can see integral, this entire thing is just this, and which finally evaluates to this thing here. And then you can just expand, you can find the value of this e power 2 pi I by 3, e power 2 pi I by 3. You can take this guy inside, it will just be 4 pi I by 3 and e power 2 pi I by 3, and then you will get this is the final value. Now let's do a more general version. You see, obviously we can generalize this thing from here. Just think of it, choosing the contour instead of e power, choosing the contour with an arc angle of e power 2 pi by 3. If I choose the contour to be an arc of angle e power 2 pi by n, e power 2 pi I by n, then I will be able to include just one pole, which is what I want, so that my calculation become easier. So as I choose the pole to be a contour of e power 2 pi, to be an arc of like this, you see, my arc I will always choose it to be, this angle will always be e power 2 pi I by n. I mean such that this point is e power 2 pi I by n, this point is well, this is r, this point is 0. So this thing will help me to pass on through these same calculations, so that only the residue factor will change. Because you see now, now you see the residue is just given by this limit z tending z naught, which is just the first root of this. So x power n equal to -1, the first root lies in I pi by n. Then you get the extra factors, you see, I pi by 3, then I pi, then you go on. So that helps me to generalize this principle to give this. You can just sit and check that this works, and then finally from here I can find the integral to be this, where I just again evaluated everything. I put this on the denominator and then simplified the expression. So hence this is our final result. Okay, now you see, suppose you have 1 plus x power 117. So that is just this much. You can plug in your values and check this is close to 1. It is not exactly up to, it will be I think 4 decimal places, and then there will be 217 or something like that. So this is the final answer. So I hope this was clear. This really helped in showing nice contour methods. I mean, you must understand that what we are trying to achieve is that we are trying to keep only one pole, the first pole, inside the contour. So if you have even e power I pi by n, if this is e power I pi by n, then if you choose a contour, the contour must be such that it should just include this pole and be done with it. And most general way to do that is choose a contour of the angle e power 2 pi I by n, as this will always be less than the second factor that will come up. You can see it from here, because if I substitute 3 as n, then I will get e power I pi by n, then e power 2 pi m by n ratio. So well, I think this was clear. So that's all for this video.